Hi, this is Todd June at OP-TEC, the National Center of Optics and Photonics. Let's look at Course 2, Lasers and Applications. And what we want to do is look at the equipment we have for the very first lab. You can see I already have my optical rail attached to my workbench here. First thing I would like to show you is we have a transformer, so it will match the power supply that we'll be using for this kit. This is a PI and MICO system, and let's get our power supply out. Set that to the side here. We are dealing with class 4 lasers, so we'll be having a key switch here that we'll be using later with an infrared viewing card. And each one of these parts are labeled, so you'll be able to follow along in the instruction guide and know exactly where each part goes. This is labeled Part 2, and this is an actual laser pump diode. We're going to assemble that on our rail here. Here's part number 4, our collimating lens. Part number 5, the focusing optic. Part number 6. This will hold our ND-YAG rod. Here's our ND-YAG rod. I want to take the cover off. Our output coupler. Part number 6 and 7 make up our resonator cavity. Part 8, filter holder. Part number 9, our target assembly. This is your initial setup for your diode pump solid-state neodymium YAG. You want to check with your manufacturer to find out the best recommendations for alignment. Once you have your laser aligned, you're ready to move on and work in your laboratories. After we've aligned our laser, we want to spend some time doing some measurements to complete the first couple of data tables. What we're really looking at is the overall goal here is to look at the optical power coming out of our pump laser, as well as the optical power coming out of our neodymium YAG cavity. So the first thing I'll recommend is that we want to measure the output of our pump laser, and that operates at 808 nanometers. So adjust your power meter accordingly and take those measurements. Then measure the output of the neodymium YAG laser and look at those measurements compared to the changing current. So what we want to look at is we want to look at the power that goes into the neodymium YAG crystal from the pump laser, and then measure the output power of the neodymium YAG cavity. Your neodymium YAG cavity will be operating at 1064 nanometers. So again, you will need to adjust your wavelength on your power meter to make sure that you are reading it correctly. And you'll also want to use your RG1000 filter to block out any of the wavelengths that are below 1000 nanometers. The last part of the experiment, we used the 808 nanometer pump laser, and we put that into a neodymium YAG cavity, and we increased the wavelength. What we want to do in this part of the experiment is introduce another crystal, a KTP crystal, sometimes known as frequency doubling, and that will shorten the wavelength. And as you can see from our cavity is we have a bright green wavelength, and we're going to do a similar experiment where we adjust the current and take an optical power reading. As we optimize our cavity power, we have 3 degrees of freedom with our KTP crystal, which is inside our resonator cavity. We can adjust the tilt, rotate the crystal, and adjust X and Y. So once we optimize our optical output, we want to fill out our data tables. If you look at your previous data table, you should have your drive currents as well as your neodymium YAG output at 1064 nanometers. And then we want to compare that to what our output is for the frequency doubled 532 nanometer wavelength. As we finish laboratory 2-1, we've removed the KTP crystal and corresponding optic and replaced it with a Q switch and its optic. As you can see here, we have a demonstration of what is the output of our neodymium YAG signal. It is Q switched, and we can look at how it looks. We can measure the pulse width, rise time, fall time, and all the corresponding questions that they're asking for in the data table. And as I adjust the diode pump current, it changes the signal. So I would take opportunity to adjust the current and see how that affects your single pulse of a Q switch, and also look and see how the adjustments of your X and Y and your tilt also affect that signal. As we observe the pulse repetition rate, we'll also see what's happening with the other parameters of the pulse, including what the average power would be, the energy per pulse, pulse width, and peak power. I want to encourage you, as you look back on laboratory 2-1, is that you realize is that this lab is actually designed to last for 3 weeks. So you'll be getting a lot of information conceptually as you go through the lecture, but also as you look at the labs, you'll be getting some hands-on experience with a very sophisticated laser, which will help the technician and all the information they'll need to learn as a laser technician.